All right. Well, this week we're going to be talking more about hypothesis testing, but this time it's going to be on comparing two populations. In specific, we talked last time about comparing paired data, and in this example, we're going to be considering only examples of non-paired or matched data, sometimes called independent samples. Okay. And our goal is to compare two population means. Okay. So here's the scenario that we want to consider. Okay. We want to know if the mean of population 1 is equal to the mean of population 2. So this is always going to be our null hypothesis, a statement of equality. And we will have one of the following forms of the alternative. Either one of the means is greater than the other, or one of the means is not equal to the other. It could be greater than, it could be less than. Now you might be wondering, is there a third form of the alternative, which is that mu2, the mean of population 2, is greater than the mean of population 1? Yes, that is possible. However, it's just a convention what you call population 1 and population 2. So these two forms are sufficient. Okay. So when you're comparing two populations, it's good to check that you have met all the assumptions necessary for comparing two populations. Okay. So in the following example, we have non-paired or independent samples, and for each sample of the population, we need to know that they're representative. Okay. And that being that the sample of population 1 comes from a simple random sample or a designed experiment. The second assumption is that the samples are independent. The outcome of population 1 or treatment 1 is unaffected by the treatment of population 2 or outcome of population 2. And each population should ideally have a sample size of 30 or more, or the observation should be relatively normally distributed. And you can assess that with a box plot and/or histogram. Okay. So under these conditions, we will use this statistic. Okay. That is the mean of population 1 minus the mean of population 2. And then we'll subtract the difference in means, the mean of population 1 minus the mean of population 2. And the standard error is given by the sample standard deviation of population 1 squared divided by its sample size plus, and I'll make that plus a little more obvious, plus the sample standard deviation of population 2 squared divided by its sample size. And that has a t-statistic. And this t-statistic, it has degrees of freedom, and it is the smaller of n1 minus 1 and n2 minus 1. Okay. Now, I'd like to state under the null hypothesis, the mean of 1 minus the mean of 2, these two means are equal. And if you subtract equal means under the null hypothesis, you get 0. So our t-statistic boils down to this. Okay. And I'll make that plus a little more obvious again. So we're going to use this t-statistic to compare population means. Okay. And we can test hypotheses and construct confidence intervals. So here's how you construct a confidence interval. When you're comparing two populations, you can calculate a confidence interval for the mean difference. You take the mean of 1 minus the mean of 2 plus or minus the t-distribution with alpha over 2 and a degrees of freedom times this standard error, S1, the sample standard deviation of 1 squared divided by its sample size plus the standard deviation of population 2 divided by its sample size. And you use that the degrees of freedom is the smaller of the two groups and subtract 1. Okay. Okay. Now, if I'm going to compare two group means via a hypothesis test, here's an example of doing that. A nutritionist wants to know if a low-carb diet is more effective than a high-protein diet. To test this claim at the 5% level of significance, a random sample of 50 is taken, and we have 25 individuals that are randomly assigned to each group. We assume the data in each treatment group is normally distributed. The results of each group we're going to look at on the next slide, but the first question is, what is the null hypothesis and what's the alternative hypothesis? So the null hypothesis is always a statement of equality, that the two diets are equally good. And the alternative is what the nutritionist suspects. They believe that the low-carb diet is more effective than the high-protein diet at losing weight. So that should be specified. Okay. And here's the data to support this claim. So we have our study here, the low carb and the high protein, and here's the sample mean of weight lost. So for the low carb, it's 5.5, so it's higher, and for the high protein, it's only 4 pounds. Now the sample standard deviation is higher in the low carb, and for the high protein, it's only 3 pounds. Okay, our sample size is 25 each. Now notice we don't have a paired data. There's not an individual like a twin in the low carb versus high protein. So there's not someone we can naturally compare. So this methodology is a bit different. Okay. So we're going to use the t-statistic, and it has n-1 degrees of freedom, so 24. Okay. And the t-statistic has the form of having an observed value minus the hypothesized value, and then we divide by our standard error. Here, our observed value is the difference in means. It's 5.5 minus 4, which is 1.5. The hypothesized value of this difference is 0, since this is our null hypothesis. Okay. And our standard error is given by this, and we just plug in the given information, and we calculate that's 5.83. Okay. Now we go ahead and we test this hypothesis, and we use the p-value method. So here I'm going to use the greater than symbol, and that greater than symbol comes from the fact that the alternative is a greater than. That mean 1 is greater than mean 2. So I'm going to calculate the probability a t-distribution with 24 degrees of freedom is bigger than 1.05 divided by 5.83. That's 0.25. And that gives me a value of 0.40. Okay. And I'll show you how I got this 0.40 in the online calculator. So if I go to the online calculator, I'm going to use the t-distribution. And the t-distribution, its value is this 0.25. And I have 24 degrees of freedom. And I'm going to calculate the two-tailed. So the two-tailed, because it's two-tailed and I'm only using a one-tailed test, I need to divide this by 2. So 0.8 divided by 2 is going to be 0.4, or roughly 40%. Now 40%, that is bigger than the p-value that's specified, which is 5%. Okay. So we fail to reject the null hypothesis. If you use the critical value method compared to the t-statistic, okay, the t-statistic that corresponds to having a 5% probability is 1.71. And since 0.25 is not in the rejection region of 1.71, it's less than the rejection region, we fail to reject the null hypothesis. Okay, so if I go ahead and use this online calculator, but now I use the inverse t-distribution. And let's see, I want to test this at the 5% level of significance, and that's one-sided. So for a confidence interval, I need to multiply that significance level by 2, corresponds to a 90%. And the degrees of freedom were 24, so I'm going to get this 1.71. That is the critical value for the t-statistic, and it's not bigger than that critical value, so I fail to reject it. Now, my suggestion is just to use the p-value, but you're welcome to use the critical value if you prefer. I suggest you do what works for you. They're both equivalent. Okay. Now, here's another example. We have a sociologist that believes that males have a higher wage than females, and to test this hypothesis, a random sample of 50 males and 35 females is taken. It's found that the average hourly wage for females is $19.25 per hour with a sample standard deviation of 3, while for men it's $20.75 per hour with a standard deviation of $4 per hour. So we want to test this hypothesis at the 5% level of significance. Our null hypothesis that the two groups make the same salary, that the two groups have the same salary. The alternative is that men make more than women, and that is the hypothesis of the sociologist. Okay. So we have this information. We have the observed value, which is the observed difference in means. It's 20.75 minus 19.25. It's $1.5 per hour. And the hypothesized value under the null is 0. Okay, so is this difference due to random chance, or is it due to the fact that men make more than women? And that's the hypothesis that we want to test. Okay, so we go ahead and calculate the standard error. We plug in the numbers 3 and 4, and we square them and divide by their sample size. We see the standard error is 0.759. The degrees of freedom is the smaller of the two groups, and that is the one with 35 minus 1. So we have 34 degrees of freedom. Okay. So we're going to go ahead and calculate that the t-statistic, and remember I have this greater than symbol here because the alternative is that it's a greater than. I calculate that a t-distribution with 34 degrees of freedom, so I apologize, okay, is greater than this statistic. So I calculate the statistic as the observed value minus hypothesized value, that's 0, divided by the standard error, and I get 1.79. So I need to calculate the probability a t-distribution with 34 degrees of freedom is bigger than 1.97. So let's go ahead and do that. So I'm not going to use the inverse t-distribution. I'm just going to use the t-distribution. And it's 1.97 is the value of the t. And I have 34 degrees of freedom. So I have 0.057. But that's two-tailed, so I need to divide that by 2. And I get this value when I divide that by 2, 0.0282, or 2.82%. That's less than the 5% level of significance, so we reject the null hypothesis. Okay. So now that we've rejected the null hypothesis, okay, we will estimate by how much more men are paid on average more than women. Okay, and we'll do this by constructing a 90% confidence interval, which will allow us to say what we think the lower amount is and what the upper amount is. Now, the estimated difference is just that difference in means. That's given right here. It's this $1.5 per hour. That's the estimated difference. Okay, but there's some variability. Okay, so a confidence interval says subtract the two sample averages, so that's the sample difference, plus or minus this t-distribution, and alpha is 10% because I have a 1 minus alpha, which is 90%, so alpha needs to be 10. Alpha over 2 is 5%. And I have 34 degrees of freedom. I multiply by the standard error. So I get 1.69 times the standard error. I just plugged in the information that was given here. Okay, and I take the sample difference. It tells me that the difference in wage could be as small as $0.215 or $0.21 or as much as $2.78 more per hour. Okay, now I'm gonna just backtrack here. How did I get this 1.69? So I have a 90% confidence interval, I have 34 degrees of freedom, and alpha is 10%. Okay, so 90% confidence and 34 degrees of freedom. So let's go to this t-distribution, the inverse. I want a 90% confidence interval, 34 degrees of freedom. I get 1.69. Okay, and that is exactly how I got that number. Okay, so this is just what we've talked about before. The estimated difference is $1.5 an hour. 90% confidence interval says it could be $0.21 or as much as $2.78. Okay. Okay. So here's some real life data, and researchers want to know if married or unmarried men have higher testosterone. And you're asked to state the null and the alternative hypothesis and test this at the 5% level of significance. So the null hypothesis is that marital status doesn't affect testosterone level, average testosterone level. And the alternative is that it does. It doesn't state which one is different, it just states that they're different. Now, when you have a two-sided alternative like this, you can test the hypothesis by simply constructing a confidence interval. And if the interval contains 0, then that indicates that the mean difference could be 0, and you would fail to reject the null hypothesis. If it does not contain 0, you'll reject the null hypothesis in favor of the alternative. And one thing that I want to emphasize very carefully, you can only do this if you have a two-sided alternative. Two-sided alternative is only that form. So be very careful when you use this, that you are in the setting that you can do this. Okay. So here's the data. And by the way, this data was taken from an actual study that is titled The Influence of Marital Status on Testosterone Levels. You can click on that for the article if you'd like. Okay. So here's the average testosterone, and these are the units. Okay, moles per liter. And here's the sample standard deviation for the married group is 7.2. The average is 20.1. And the sample size is very large. It's 1454. For unmarried men, the average is 22.1. The sample standard deviation is 7.5, and the sample size is a bit smaller. Okay. Now, this is only about 2 units difference, but the question is that 2 units, could that be due to random chance in the sample, or is that an actual difference in the population? So let's go ahead and test this hypothesis by constructing a confidence interval. Okay, because we can test a two-sided alternative, which this is, like I said, two-sided, by constructing a confidence interval. So let's go ahead and do that. I take the difference in the averages. I compute the standard error here, so I just plug in the numbers. Okay, and I have a t-distribution with alpha over 2. And so I want a 95% confidence interval. Alpha is 5%. Alpha over 2 is 2.5%. And I have the smaller sample size is 245. So 244 is the degrees of freedom. Okay. So let's go ahead and figure out how I got this 1.969. So I have 244 degrees of freedom, and I want a 95% confidence interval, so 1.97. Okay, that is essentially 1.97. I've used a slightly different calculator, so it's just off in the third decimal place, but it's essentially the same number. And when I go ahead and crunch this confidence interval, one thing that I see is that 0 is not contained in this interval. So I'm going to reject the null hypothesis that the two groups could have the same testosterone level, the same average testosterone level. Okay, so on average, unmarried men have a significantly higher testosterone level than married men. And that testosterone difference by the confidence interval could be as low as 0.96 or as high as 3.03 units bigger. The estimated difference is 2, the difference in these two populations. Okay, here's one more example. And this is a case study, a real data set that you've seen before. And it's a data set on employees from one job category at a bank that was sued for sex discrimination or gender discrimination. And we have data on 32 male and 61 female employees. We have all these variables, but the only one that I'm going to use is base salary, the salary at time of hire, and I'm going to use sex. So these two. And my question is annual salary at time of hire or starting salary, does that change based on the sex of the employee? Okay. Well, we have this data. It looks like this, but we're only going to really look at this. That's the starting salary. We're only going to look at this. And there are females in this group. I've just provided you with the first 6 data points. Okay. So our question is, do males earn more than females at this bank? And test this at the 1% level of significance. So this is a real data set, and I crunched this data in using statistical software. Okay, this was the command to test if it was equal. And what this is it performs the hypothesis test. It tells me the t statistic, tells me its degree of freedom, and its p-value. Okay, so one thing you should notice, the degrees of freedom, it uses a slightly different method. You can ignore that. You'll get relatively the same result if you were to use the method that I have prescribed in this book. Okay, but this t statistic, it calculates for you. That's the observed difference minus the hypothesized difference divided by the standard error. And it tests the hypothesis that the two starting salaries are equal. Okay, so the starting salaries of males and females are equal. And the alternative hypothesis is that the difference in the starting salary, the average or population mean starting salary, is not equal to 0, meaning they're not the same. And it returns to us a p-value of 3 times 10 to the negative 7th. I can reject this at almost any level of significance up to 3 times 10 to the negative 7th. So I can reject this at the 0.01% level of significance. It is virtually statistically impossible that the difference in these starting salaries is due to random chance or a bad sample, and that it's more likely that sex plays a difference in starting salary. The confidence interval is that the estimated difference in starting salary could be as large as $1,099 or $1,100 that males earn more, or as low as $536. Okay, the estimated mean starting salary of females is going to be $5,138, and for males it's $5,956. The estimated difference is just the difference in these two sample averages. Okay, and here I just re-emphasize exactly what I just said. Okay, So that is all that I have for comparing two population means. We'll continue this discussion next time, discussing population proportions.